examples and discussions about motion in space. In particular, we're going to talk about applications involving velocity and acceleration, and some interesting connections with the stuff we did in the previous lessons, like the normal or the tangent, the curvature, and things like that. So to an extent, actually, some of the topics of today's lesson were discussed or mentioned, at least in passing, in the previous sections. So it's not really, nothing is really new from a calculus standpoint. We just go through applications related to the situation in which the vector function is describing a motion in space. So be aware, as a general remark, that from now on, same mathematical object can mean different things in different contexts, and it will also have different notations in order to be more suggestive in that context. So let me explain what I'm talking about, right? So once again, starting with the vector function, if let's say in 3D, right, given by 3 component functions, if this denotes a motion in space, then the tangent vector, which of course is the derivative of this vector function, is also the velocity vector in the context of a motion, right? So the velocity obviously gives you the direction of motion, where you go at that point, and how fast you go. And the rate of change of the velocity, how fast the velocity changes, as you might know already, is called acceleration, which is another vector. Notice that prior to studying vectors, sometimes people would use the word acceleration to mean the magnitude of the acceleration. But from now on in this class, let's try to be picky and not confuse the vector with the magnitude, right? So both of these are vectors. And of course, the rate of change of the velocity is going to be the second derivative, right, of the original vector function. Something is wrong here with my pen. So r of t here on the top, r of t, f of t, g of t, h of t. So because we talk about velocity and acceleration, it's worthwhile, of course, to have different notations which are more suggestive, right? So obviously the velocity vector typically is denoted by v bar of t, but remember this is nothing but v bar of t, but remember this is nothing but r prime of t. Okay, and then consequently the a bar of t, the acceleration, is nothing but the first derivative of the velocity, which is of course the second derivative of the original vector function. Speed and magnitude of the accelerations are scalar related to these vectors, right? So speed at time t, we typically denote it by script v of t, which is the magnitude of the velocity. Of course, the same as magnitude of the unit of the tangent vector. And then the magnitude of the acceleration, it's a scalar a of t, which is the magnitude of a bar of t, which of course is the same as the magnitude of v prime of t, which is the same as the magnitude of r double prime of t. You don't have to go with all of these alternative notations, but I'm mentioning them here so that you always have them in mind, right? I mean, that's to make connections, right, with different notations depending on the case. So let's start with an example right away, starting with a 2D example. So suppose, for instance, the motion is described by the position vector of that object in the plane. We're talking about a space curve, a curve in the plane. By the position vector r of t equals components 2 minus t 4 square root of t. You may notice also that in applications like this, because I said before, I don't prefer usually if I have a choice, to use the standard basis, but this is one of those exceptions in which most of the time it's more practical to use maybe the standard basis. I mean, actually, I don't know if it's more practical, it's just an alternative, but I noticed that in many books, when it comes to motion, this type of problems, they tend to use the standard basis notation for a vector in component form. So I'm going to use that here as well for a couple of examples. By the way, remember, just as a quick recollection, right, in 2D, ij are 1, 0, 0, 1, right? And let's say the question is to find, just a basic question to begin with, let's say we need to find the velocity and the acceleration at t equals 1. Let's say we want to find this at the time t equals 1. So obviously you differentiate first, right? So v bar of t is going to be r prime of t. And like I said, let's use the standard basis. When you use the standard basis, you can think of I and j as being constants essentially, right? I mean, because all of the differentiation rules hold in an analogous fashion, like in calculus 1. You really have a scalar product here, right? But to minus t and I, but all derivative rules hold in the sense that you can pull up the constant, which is the vector I, and then differentiate to minus t. So therefore, the velocity vector is going to be minus I plus the derivative of 4 root t, which is going to be 4 times 1 over 2 root t. That makes it 2 over root t j. And at t equals 1, now you can plug in the time 1 for t. That's going to be minus I plus 2 over 2j. If you want to compute the speed at that point, obviously that's the magnitude of this vector, which is square root of 1 plus 4 square root of 5, and you can call it meters per second or whatever the units are for the speed in this problem. In general, speed as a function of t, if you need that, that's going to be just the magnitude of this in terms of t, so that'll be square root of 1 plus 2 over root t quantity squared, which makes it 1 plus 4 over t. So let's compute the acceleration. Acceleration at t obviously is the derivative of velocity. I look at the velocity in terms of t, which is over here, and differentiate one more time, and that'll give me 0 times I. So see, minus I is like a constant, so it's going to be basically the 0 vector. Or you can just not mention it, right? Because it's 0, right? It's not going to have any effect on the addition here. And then the derivative of 2 over root t, that's 2 t to the minus 1 half. If I differentiate that, minus 1 half t to the minus 3 halves j. So in terms of t, the acceleration at time t is going to be minus t to the minus 3 halves j. So if you stick to component forms, I guess one disadvantage is that you have to track those zeros, right? Because the I component now is 0. At 1, at time equals 1, the point in question, that's going to be minus j, right? Or in component forms, 0 minus 1. So the acceleration at 1 is 0 minus 1. The velocity at 1, at time t equals 1, is minus 1, minus I 2j. In some problems, you're asked to sketch these vectors. Let's just do a little sketch here. This is the planar vector. If you imagine I'm going to sketch the curve later. I should have plotted here before with Maple, but anyway, let's just sketch the vectors, and that's it. And just imagine a portion of the curve going through that point. So the velocity, so let's say at t equals 1, the velocity is minus 1 and 2, right? So that means, let's say this is minus 1 over here and 2. Well, let me take a step back for a second, because the point itself, remember, these are vectors in the component form, but you do not need to. Let me actually figure out. Let's actually start with the position vector. Let's do that first. Let's do the position vector as well. So r of 1 equals, because I said t equals 1, right? Yeah, 2 minus 1, which is 1, and 4 square root of 1. Okay, so let's start with the position vector, because that's where you place the tangent vector, right? I mean, you're not going to put all of these vectors from the origin. You have to put them from at the place where the motion takes place, right? So r of 1 is 1, 4. Let's say this is 1, 1, 2, 3, 4. You know what? Let me actually do it here. I have more room here before I move on to the next page. Make the units a little bit smaller. So let's say this is 1, 1, 2, 3, 4. So that's the position vector. The tangent vector, which we're going to place at this point, the tangent vector, which is v of 1, the velocity is minus 1, 2. So remember, in component force, that means you move 1 unit to the left, 2 units upward, right? So minus 1, 2. Tangent vector is going to be somewhere here. Let's try to do it with a different color. That's the velocity. So for example, suppose the curve maybe is like that, you know, so the vector is, velocity is tangent to the curve. And then the acceleration, which you're going to start it from the same point, again, that will indicate how fast the velocity will change. It's 0 minus 1. Let's do this with blue. That means the x component is 0, y component is minus 1. So it's downward, vertically downward, like that. Yeah, doesn't look too pretty. Right? V of 1, and this will be A of 1. Okay, so I'm not going to sketch the curve. Let's not bother with that. I just put it here because I think 1 or 2 problems in the homework will ask you to come up with these vectors. The key thing is that make these vectors both v and a to originate where the actual mobile is located, right? Given by the position vector, right? So which I put it here, right? From the origin. All right, let's move on to the next example on the second page. Okay, so let's do an example which starts from the acceleration, and the question is to find the velocity and the position vector. So this is basically the opposite problem, in which you're gonna integrate the acceleration, right? Because you go in reverse. So find the velocity and the acceleration, and the position vector if the acceleration of that mobile is a bar of t equals, so let's do a 3D example, 2i plus 6tj plus 12t squared k. And we need to have some initial conditions, because remember, with integrals we have constant of integrations. So let's say v of naught is I, which remember really stands for 1, 0, 0 in this case. And r of 0, the position vector at time 0, is j minus k, which really means that's 0, 1, minus 1. But again, let's use the ijk representation, the standard basis representation. This will mirror again the whole concept, the whole type of this, the same type of problem you did in calculus 1, right? With when you have an acceleration, so you do integral twice, right, to get to the velocity and then to the original position vector. So because the velocity is equal to the integral, the antiderivative of the acceleration, that means we have to integrate the acceleration. Same rules apply, right? We distribute the integral to each component. So the antiderivative would be 2ti plus 3t squared j plus 4t third k plus a constant of integration, but notice that the constant of integration is a vector in this case. That's the difference from calculus 1. How do we find the constant of integration? Well, we're going to plug in 0 for t in order to use the first initial condition. So v of 0, that'll make 0 ijk in this case. So v of 0 happens to be just c bar, and that's equal to I. So when we come back here and plug in the constant of integration, plus I, of course, we have to combine the components, right? We need to give the answer as a vector. So now the I component is 2t plus 1, and then followed by 3t squared j plus 4t third k. Remember to pause and do the computation on your own, maybe ahead of me, to check the answer. For example, why don't you stop the video now and do this, find the position vector yourself, which is just a repetition of the same type of step, except now you integrate the velocity in order to get the position vector. So repeat the whole process and see if you get the same answer as mine. All right, so let's do it. The integral of v of t, that's again component by component, t squared plus t I plus t third j, and then plus t fourth k, and then again another constant of integration. We can still call it c because we're going to find it immediately. It doesn't have to be the same. Well, actually, let's so we avoid any confusion, let's call it d. And then that comes again from the initial condition, which in this case is r naught is equal to j minus k. But r of 0, not r naught, r of 0, again it's going to be 0 plus d. So therefore d is going to be j minus k. So just like before, we're going to plug in back this constant of integration into the answer. And then combine all the components together. T squared plus t I, j combines into t third plus 1, and then finally k, this component is t fourth minus 1. So I hope this rings a bell in terms of a technique. You did something like that in calculus 1, with the only exception that you dealt with single variable functions, but the procedure was the same, right? So these are relationships between velocity, position vector, velocity, acceleration. Now, something a little bit more interesting in the sense that not related to anything in calculus 1 or 2 that you have done. It's something called the tangential and normal component of acceleration. This is another application which is not, I wouldn't say it's hugely important. We're not going to meet with it from the after this lesson, but it gives me yet another opportunity to go through the previous concepts, because the derivation of this formula, it's a formula what I'm talking about now, the derivation of the formula is a nice refresher exercise on its own. You might notice as you go through the course that I prefer to go through the proofs if they're not too complicated and if they are worthwhile in terms of reinforcing what we did before. So the subtitle, like I said, is the so-called tangential and normal components of the acceleration vector. So there is a relationship between the acceleration and the unit tangent and unit normal that are interesting in the sense that they can give you a quick insight into how these vectors look like depending on the type of motion that you have at hand. So let's remember, and we did this before, but let's write those objects with different notations. So let's remember that the definition of the unit tangent is r prime of t over its magnitude. But with the notations related to the motion in space, this is nothing but the velocity vector divided, or that is to say scalar multiple, by 1 over its velocity. Right? Remember that v of t is the velocity, script v of t, it's the, not the velocity, the speed. Script v of t is the notation for the speed. So 1 over the speed, scalar multiple v of t. Furthermore, remember that the normal is the derivative of the unit tangent over its magnitude of the derivative. Magnitude of the derivative of the unit tangent is not unit, it's not equal to 1. And I'm going to again put another formula here. You might remember the curvature at the point is the magnitude of the unit tangent divided by the magnitude of the r prime of t, right? So this is the curvature at that point, which using the notations from the motion in space, the bottom here is nothing but the speed, v of t. And on the top, I'm going to keep t prime of t. Okay, so with these notations, I want you to take a look at the first equality over here. And notice that this tells me, unsurprisingly, that the velocity is the scalar multiplication between the speed and unit tangent. Speed, scalar multiplication, unit tangent. I'm saying not surprisingly because remember, unit tangent gives you the direction of motion without taking into account the speed. So of course, if you multiply the vector that gives me the direction with the speed, that gives me the velocity by definition. The velocity tells you where you go and how fast you go. So it encapsulates both of these components. Let's use this equality actually to derive the acceleration. So the acceleration vector, remember, is the derivative of the velocity. And by the product rule on the above equality, this is going to be script v prime of t, right, the derivative of the speed, scalar multiple with the unit tangent, plus v of t scalar multiple with t prime of t. Nothing but the product rule, which still holds for scalar multiplication. All right, so we're going to keep the first term as it is. And for the second term, I'm going to replace t prime of t with its normal relationship, like from the second equality here that I circle right now. So that means the t prime of t is the scalar multiplication between the magnitude of the t prime of t and the unit normal. Again, try to follow carefully and realize that the scalars are always in front of the vectors, right? So this is still a scalar. And remember, I want tangential and normal components. So the goal is essentially to write the acceleration in terms of the unit tangent and the normal. So we're nearly done, because now, finally, I'm going to use the last equality, the one with the curvature, and express the derivative of the unit tangent in terms of the velocity, the speed, and the curvature. So the acceleration, let's write it one more time here. It's v prime of t unit tangent, v of t, speed, magnitude of t prime from the last equality is curvature times the speed again. So another speed times the curvature, and then finally scalar multiplication with the unit normal. So when I put all of these together, I arrive to the formula that I was looking for, the normal, tangent and normal components of the acceleration. V prime of t, t of t plus k of t, v squared of t, n of t. I like usually to write drop of t. Again, remember, you should always do that as a matter of practicality. If everything depends on t and you know clearly that that's the case, you don't have to write of t all the time. Right? So here's a more compact way of writing this formula. So let's talk about the meaning of this formula. Right? It tells you basically that wherever you are in the motion on a curve, the acceleration is going to be essentially a linear combination of the unit tangent and the unit normal. So how much each component is depends on the curvature and the speed, right? So how much each component is on each direction. So in other words, if I were to, imagine, for example, this is the motion here, and this is my unit tangent. Let's say this is the normal. I'm not going to sketch the binormal, right? The acceleration is always some multiple of the unit normal, some multiple of the unit tangent, and then when you add them, add the two of them as a vector, that'll give you the acceleration vector. So it's always the sum of two vectors, a scalar multiple of the tangent, unit tangent, a scalar multiple of the unit normal. So you can derive some interesting observations here from this formula. So for example, let's write these as remarks. For example, what can I say if, let's say, if the speed is constant? What can I say about the acceleration? Well, if the speed is constant, that means v prime is 0, right? The derivative of a constant is 0. So that means in that case, the acceleration is always parallel to the normal. Now, for example, this correlates, for instance, with the satellites, okay, or naturals or artificial, right? So if you have some constant orbital speed, then as long as the speed is constant, the acceleration is along the normal. And that's not something intuitive you know already, because the acceleration is the gravity in that case, denoted by g, right? And that's always in the direction of the normal. Again, if the speed is constant. What if the trajectory is a straight line? Straight line trajectory. Well, if it's a straight line trajectory, there's no turning on that straight line. That, another way of saying this is that the curvature is 0. So if that's the case, then there is no normal component. So in that case, the acceleration and the unit tangent are parallel. So when you move on a straight line, the acceleration is in the same direction as the motion itself. So with that being said, these are all the topics that we covered in this class, in this lecture for today. I want to actually dedicate another page for this lesson because there is a nice problem I usually assign to the students, and I want to do just a portion of it. It's actually from the book itself. Let's see, I got the number. It's problem 29 from this section. I want to do just a portion of it, give you the answer, and then leave half of it for your enjoyment to do. I think it's a nice problem, not a short one, but it's a nice one to discuss. So I'll conclude with that on the last page. So stay tuned. All right. So this is a rough description of the problem, not verbatim, from that section. I'll draw a picture which is going to be more suggestive once we read it. So let's take a moment to write it down and read it together. So let's pinpoint the important information here. Okay, so we have a gun. By gun, we in this context means a piece of artillery that aims to fire a projectile into an enclosure, right? So the goal is to basically have that projectile land in a certain area, which is demarcated by two walls, and the gun is 100 meters to the near wall and 500 meters to the far wall. So basically the enclosure is 400 meters apart. I forgot to mention here in the problem, because we need that as well, the height of the walls is 15 meters. Okay, so we have the dimension of the enclosures essentially. We have the initial speed of the projectile. Keep in mind the initial speed of the projectile. The question is, at what angle should we set up the gun? To raise the gun so that the projectile lands in the enclosure. I don't know how complicated this problem looks like. It depends on those of you who took physics classes might have done stuff like that, problems like this before. But if you didn't do it before, it might have an interesting, surprising result to you, in the sense that you will see that the answer is not actually a precise number, but a range. And it's not a fixed angle. So there are essentially two possible ranges in fact. Not only it's not a fixed angle, there are essentially two sets of ranges for these angles so that you achieve the goal. And this connects with some interesting historical aspects, like for example, I'm going to talk about later after we go over the problem itself. Which range would you choose? The one with higher values or lower values? And that has some interesting connections with military history. But let's see how we can do the simplest possible sketch to represent the problem here. So since everything can be described via a planar system, if you think about it. So let's place the gun at the origin of the coordinate system. So this is X and this is Y. And suppose that this is the near wall, 100 meters away from the gun, and then the far wall 500 meters. So these are the walls here. And we want, of course, for the projectile to land in between, right? So that's the enclosure. And let's see if I can do this without making too much of a mess in my picture here. Now, why would you have actually a range of angles? Well, obviously, since the projectile can land anywhere in between these points, clearly there's no fixed angle, right? But how do you figure out the range so that you fit the projectile between the two walls? So there are two requirements essentially. So you want to pass the near wall, so you don't want to shoot too short, you have to pass the near wall, and you don't want to overshoot the far wall. Now once you fire the gun, so let's say let's denote by alpha the angle, the initial angle, which means in the velocity, the initial velocity v of 0, well, the initial, it doesn't say velocity, the initial speed v of 0 is going to be 80 meters per second. So let's call v bar of 0 the initial velocity. We're going to come up with that vector in a minute, right? But whatever that initial vector looks like is going to look like this, right? V bar of 0. And then as the projectile moves in the air, the only force that acts on it is going to be the gravity, the gravitational force. And remember, in meters per second, the gravitational acceleration, we know that from physics, is denoted by g, which is 9.8 meters per second squared. When I say 9.8 meters per second squared, because I said we have to be picky now with terminology, we mean the magnitude of the acceleration, not the acceleration as a vector. We'll get to that in a moment. So I'm going to go over the procedure on how to figure out the conditions so that the projectile will pass the near wall. Right? Let's do that first. So notice, imagine that you set this gun at the various angles of attack here, right? Let's denote that, like I said, that angle by alpha. If the angle is very, very small, okay, I'm going to do a little bit of a dotted line here. If the angle is very, very small, it's going to hit the wall. So it cannot be too small. It has to be bigger, so it goes past the wall. But that's one possibility of a range of angles, just for this first condition, passing the near wall. We're going to have a range of angles, obviously, right? Not too low, not too far, because if that range, if the angle is even bigger, let's say it's further, at some point in between, it's going to go in the enclosure, or it will pass the near wall. But if that angle is really big, it's going to still hit the near wall. I mean, it's going to be too high, and it's going to land again in front of the wall. So I need a range so that it's not too low to hit the wall, but not too high to also land in front of the wall. So that's going to be basically an interval for the angle of attack, just to pass the near wall. And we're going to have a similar condition, but in the opposite way, so that it doesn't overshoot the far wall. Now, intuitively, that's basically the main idea. Now, how do we figure out these ranges? Well, let's come up with some tools here. Let's put let's construct some vectors with these with the data in the problem here. We have the initial speed. Let's come up with the actual velocity vector. Now, for a vector in R2, we can just use the trigonometric functions cosine and sine for alpha in order to compute the components of that vector, of the velocity vector. So the magnitude of the velocity vector is given in the problem, right? The initial velocity. It's 80 meters per second. Let's actually call this initial velocity v naught so that it's easier to handle. By components, as a vector, v naught or v of 0 is going to be the initial velocity, the initial speed, v naught cosine of alpha, v naught sine of alpha. Right? Because the x coordinate is the adjacent side to alpha, so that's going to be hypotenuse times cosine of alpha. Like I said, during motion, the acceleration is going to be given by the just gravitational acceleration. As the projectile moves in the air, the gravity acts downward, so it has basically a 0 x component and a negative, because it's in the opposite positive direction of y, y component. So in other words, the acceleration by components will be 0 and then minus g. Or if you want to work with numbers right away, I'm going to keep using g until I need to plug it in, 0 minus 9.8. Okay? Or if you want to use, for example, ij notation, that's going to be minus g j bar, whichever we prefer. I'm going to use components probably because it's because I tend to like it better. Okay, so we have the acceleration, 0 minus g. We have everything we need. Let's come up with the velocity. Basically, we're going to have to how do we figure out the range of angles that I mentioned before? We're going to have to compute the position vector of the object and make the position vector just touch the top of the near wall and see which angles we're going to come up if we do that. And that's how we come up with the ranges for the angle of attack. So we have to go from acceleration to velocity. The velocity is going to be the integral of a of t and that's going to be let's see, well, let's actually use this, probably is much better with the ij notation. So it's going to be minus g t j plus a constant of integration, which is a vector. All right, the initial velocity vector is going to be c bar in this case, which is going to be v naught cosine of alpha, v naught sine of alpha, which is the same as v naught cosine of alpha I plus v naught sine of alpha j. Plug it back into the velocity, and we get minus gt j plus v naught cosine of alpha I plus v naught sine of alpha j. Combine the components, I get v naught cosine of alpha I plus v naught sine of alpha minus gt j. So that is the velocity as a vector. Finally, the position vector, another integral, so r of t is going to be the integral of the velocity. And because it starts from the origin, notice that r of 0 is the 0 vector, so that integration constant is going to be probably 0. Moving on, so the integral of this will be, we integrate the first component, so that's v naught cosine of alpha t, scalar multiple with I. Now integrate the second parenthesis in terms of t, that's v naught sine of alpha t minus gt squared over 2 j. Some of you who took physics before may have noticed these given as formulas, but now you know where they come from, I guess. I remember when I took physics way back when I was in middle school, I think. I remember distinctively this this component, gt squared over 2, popping up in some formulas. It was given as a formula basically, but now you just can derive it on the spot. All right, so that is the position vector. Again, from this point on, if you want to prefer to use it use it by components, you could do that. You can write it as v naught cosine of alpha t, v naught sine of alpha t minus gt squared over 2. Same idea. All right, so what happens when the position vector just touches the top of the near wall? Okay, let me emphasize it here with the red color here. So the coordinates of the top of the near wall are 115, right? Remember the height of the wall is 15 meters. So basically the first component phi naught cosine of alpha t should be equal to 100, the horizontal component, and the second component v naught sine of alpha times t minus gt squared over 2 should be equal to 15. Now v naught, of course, is given. It's 80. At this point, let's actually replace v naught with 80, g with 9.8. And we have a system in alpha and t. Remember, we have to find alpha. So we have to solve for alpha from this system. So we have t is outside cosine. Hopefully it's not too confusing. So t times cosine of alpha is 100 over 80. 100 over v naught, which is 100 over 80. We can get t by itself from here. T is going to be, let's simplify by 2. That's going to be 5, not by 2, by, what do I do that? By, we can simplify by 100 over 80. Can simplify by 20, yeah, 5 over 4. 5 over 4 cosine of alpha. So that's the t from the first equation. And in the second equation, let's plug it in. We have 80 sine of alpha. T is that we just found, 5 over 4 cosine of alpha minus g over 2, which is actually 4.9. T squared, which is 5 over 4 cosine of alpha quantity squared, equals 15. Okay. There is a little bit more computation here to be done, which is not exactly trivial. Let's see if I need to do it on the second page. We'll see. So, yeah, let's do it. I'm going to use the calculator, and you can check the computation yourself. But here the coefficients, let's see. This guy here simplifies to 100 because this is 20. So here on the first term I have 100 tangent of alpha. Here 4.925 over 16. So if I combine all those constants, I got this ugly coefficient. You're going to have to use the calculator to check yourself. You're going to get 7.65625. And then you get 1 over cosine squared, which is actually secant squared alpha. The goal is to basically get a quadratic in terms of one trigonometric function. Let me actually continue this on the next page so I don't crowd this too much here. So stay tuned for the last part. All right, so let's continue this. I copied the picture again so we can have it in front of us here. So that secant squared is because 1 over cosine is secant, right? So you can replace 1 over cosine squared with secant squared. The reason you want to do that is because finally now you can get everything in terms of tangent of alpha. Again, these are trigonometric formulas. I don't require memorization. Usually I put them in the exam if the problem needs one of these. But you might remember also from calculus too that secant squared is nothing. It's 1 plus tangent squared alpha. So basically it all boils down to a quadratic in tangent of alpha. If you actually rearrange the terms here, you can write everything as a single quadratic equation in tangent of alpha. Like that. and then combine the constant into, that combines into 22 point, if I did this correctly, 22.65. I did it with the calculator, so if you see a typo, let me know in the comments. But obviously you have to do it with the calculator, right? So now just use the quadratic formula and just solve for tangent of alpha. If you do it correctly, tangent of alpha should be equal to either 0.229 or two solutions, or 12.835. Use the inverse tangent of those values. So therefore the range for alpha will be 13 degrees or 85 degrees. Okay, so I'm gonna leave you to your own devices to do the second part. It's essentially, so for the last part, it's gonna be a repeat of the same process, but now using 615, right? Using the firewall. So let me see if I'm going to do another picture here because I want to mess around with this a little bit more. Okay, so what is this range meaning, right? And actually, let me write down the answer for the second part. That, like I said, I leave it as a homework normally. So if you repeat the process with the corner 615, the whole process, the only difference of course is going to be 600 instead of 100, right? I mean, you're going to have to figure out essentially what you get for alpha if the position vector is touching the top of the firewall. When you go through that process, you're going to get two values for alpha, namely in degrees, they will be, let me see if I have it here, 1385, you're going to get 36 and 55.4 approximately, 36 degree or 55.4. Okay, so on this new picture, let's come up again with our reasoning, right? What goes on, like what is the correct range for the initial angle of the piece of artillery? Clearly, you want to be in between the first range, 13 degrees, 18 degrees. So you want to be in between these two values just to pass the near wall, right? Lower than 30 degrees, you're going to hit the near wall. Higher than 80 degrees is too high. You're going to land on a point in front of the wall. But exactly the opposite should happen with respect to the second wall, right? So you don't want to go, of course, you don't want to go too high above the lower value, 36 degrees, because again, if you do that, you're going to overshoot it. And again, you don't want to go, let's see, what do I want to say? You don't want to go above the lower value, and you don't want to go less than the lower value because of the same reason, overshooting it, right? So, I mean, if it's high value, but not high enough in this case, you're still going to overshoot it. So you're going to want, of the second range, you want to be within that higher value, basically. So, in other words, you want to be outside the range given by the second condition, outside the range of 36 and 55.4. So let's say 36 degrees is here, 55.4 is here. Once again, above 36, you're going to overshoot it with a lower trajectory. Below 55.4, again, you're going to overshoot it with a higher trajectory. So the common part of these two ranges will give you, the common part of these solutions will give you basically two possible ranges that both achieve the same thing. So in both cases, you're going to land inside the enclosure with a low amplitude trajectory, or you can achieve the same thing but with a high amplitude trajectory. So two possible ranges for the solution. I said about military history. Well, usually high amplitude trajectories are relevant in, for instance, if you look at World War I history, World War I stories, in the trench warfare. Why? Because typically, to oversimplify the matter here, in the trench situation, right, the enemy trench is here. Typically, high amplitude trajectories you want to deal with, right? I mean, to oversimplify, obviously, it's more complicated than that, because you don't want to be too low, of course, because you're going to hit the enclosure, or your own enclosure. In fact, the mortar, as a piece of artillery, a small piece, it's always, as far as I know, it was always designed to have a high amplitude angle of attack to deal with these situations in the trenches when you actually have to go past the wall in front of you. Anyway, that's it for today. If you're not my student, you might not care about this problem, but usually I assign this problem in my class and I leave the second part as a homework. So that's it for today. Next time we're going to start our new chapter on functions of several variables. See you later.